This next equation might not look like an equation involving radicals, but in fact, we can think of a fractional exponent as being a radical in disguise. Let's start by doing the same thing we did on the previous problem, by isolating. This time, we'll isolate the part of the equation that involves the fractional exponent. So I'll start with the original equation, 2 times p to the 4/5 equals 1/8, and I'll divide both sides by 2, or equivalently, I can multiply both sides by 1/2. That gives me p to the 4/5 equals 1/16, and I've effectively isolated the part of the equation with the fractional exponent as much as possible. Now, in the previous example, the next step was to get rid of the radical. In this example, we're going to get rid of the fractional exponent. And I'm going to actually do this in 2 stages. First, I'm going to raise both sides to the 5th power. That's because when I take an exponent to an exponent, I multiply my exponents, and so that becomes just p to the 4th equals 1/16 to the 5th power. Now I'm going to get rid of the 4th power by raising both sides to the 1/4 power, or by taking the 4th root. There's something that you need to be careful about, though. When taking an even root, or the 1 over an even number power, you always have to consider plus or minus your answer. It's kind of like when you write x squared equals 4 and you take the square root of both sides, x could equal plus or minus the square root of 4, right? X could equal plus or minus 2, since minus 2 squared is 4 just as well as 2 squared. So that's why when you take an even root, or a 1 over an even power of both sides, you always need to include the plus or minus sign. When it's an odd root, or 1 over an odd power, you don't need to do that. If you had something like x cubed equals -8, then x equals the cube root of -8, which is -2, would be your only solution. You don't need to do the plus or minus because +2 wouldn't work. So that aside explains why we need this plus or minus power. And now p to the 4 to the 1/4, when I raise a power to a power, I multiply by exponents. So that's just p to the 1, which is equal to plus or minus 1/16 to the 5th power to the 1/4 power. Now I just need to simplify this expression. I don't really want to raise 1/16 to the 5th power, because 16 to the 5th power is like a really huge number. So I think I'm actually going to rewrite this first as p equals plus or minus 1/16. I'll write it back as the 5/4 power again. And as I continue to solve using my exponent rules, I'm going to prefer to write this as 1/16 to the 4th root to the 5th power, because it's going to be easier to take the 4th root. Let's see, the 4th root of 1/16 is the same thing as the 4th root of 1 over the 4th root of 16. Raise all that to the 5th power. 4th root of 1 is just 1, and the 4th root of 16 is 2. Raise that to the 5th power. That's just going to be 1 to the 5th over 2 to the 5th, which is plus or minus 1/32. The last step is to check answers. So I have the two answers, p equals 1/32 and p equals minus 1/32. And if I plug those both in, 1/32 to the 4/5 power, that gives me 2 times 1 to the 4/5 power over 32 to the 4/5 power, which is 2 times 1 over 32 5th rooted to the 4th power. 5th root of 32 is 2. Raise that to the 4th power, I get 16. So this is 2 times 1/16, which is 1/8, just as we wanted in the original equation up here. Similarly, we can check that the p equals negative 1/32 actually does satisfy the equation. I'll leave that step to the viewer. So our two solutions are p equals 1 over 32 and p equals minus 1 over 32. I do want to point out an alternate approach to getting rid of the fractional exponent. We could have gotten rid of it all in one fell swoop by raising both sides of our equation to the 5/4 power. 5/4 is the reciprocal of 4/5. So when I use my exponent rules and say that when I raise the power to the power, I multiply my exponents, that gives me p to the 4/5 times 5/4 is plus or minus 1/16 to the 5/4. In other words, p to the 1 power, which is just p, is plus or minus 1/16 to the 5/4. So that's an alternate and possibly faster way to get to the solution. Once again, the plus or minus comes from the fact that when we take the 5/4 power, we're really taking an even root, a fourth root, and so we need to consider both positive and negative answers. This video is about solving radical equations, that is, equations like this one that have square root signs in them, or cube roots, or any other kind of radical. In this video, we solved radical equations by first isolating the radical sign or the fractional exponent, and then removing the radical sign or the fractional exponent by either squaring both sides or taking the reciprocal power of both sides. This video is about solving equations with absolute values in them. Recall that the absolute value of a positive number is just the number, but the absolute value of a negative number is its opposite. In general, I think of the absolute value of a number as representing its distance from 0 on the number line. The number 4 and the number -4 are both at distance 4 from 0, and so the absolute value of both of them is 4. Similarly, if I write the equation the absolute value of x is 3, that means that x has to be 3 units away from 0 on the number line. And so x would have to be either -3 or 3. Let's start with the equation 3 times the absolute value of x plus 2 equals 4. I'd like to isolate the absolute value part of the equation. I can do this by starting with my original equation, subtracting 2 from both sides, and dividing both sides by 3. Now I'll think in terms of distance. On a number line, the absolute value of x is 2/3, means that x is 2/3 away from 0. So x could be here or here, at -2/3 or at 2/3. And the answer to my equation is x is -2/3 or 2/3. I can check my answers by plugging in. 3 times the absolute value of -2/3 plus 2, I need to check if that equals 4. Well, the absolute value of -2/3 is just 2/3, so this is 3 times 2/3 plus 2, which works out to 4. Similarly, if I plug in positive 2/3, it also works out to give me a correct answer. This second example is a little different because the absolute value sign is around a more complicated expression, not just around the x. I would start by isolating the absolute value part, but it's already isolated. So I'll just go ahead and jump to thinking about distance on the number line. So on my number line, the whole expression 3x plus 2 is supposed to be at a distance of 4 from 0. So that means that 3x plus 2 is here at 4, or 3x plus 2 is at -4. I'll write those as equations. 3x plus 2 equals 4, or 3x plus 2 is -4, and then I can solve. So this becomes 3x equals 2, or x equals 2/3, and over here I get 3x equals -6, or x equals minus 2. Finally, I'll check my answers. I'll leave it to you to verify that they both work. A common mistake on absolute value equations is to get rid of the absolute value signs, like we did here, and then just solve for one answer instead of solving for both answers. Another mistake sometimes people make is once they get the first answer, they just assume that the negative of that works also. But that doesn't always work. In the first example, our two answers were both the negatives of each other, but in our second examples, our two answers were not just the opposites of each other. One was 2/3 and the other was -2. In this third example, let's again isolate the absolute value part of the equation. So starting with our original equation, we can subtract 16 from both sides and divide both sides by 5, or equivalently multiply by 1/5. Now let's think about distance on the number line. We have an absolute value needs to equal -3. So that means whatever is inside the absolute value sign needs to be at distance -3 from 0. Well, you can't be at distance -3 from 0. Another way of thinking about this is you can't have the absolute value of something and end up with a negative number. Absolute value is always positive or 0. So this equation doesn't actually make sense, and there are no solutions to this equation. In this video, we solved absolute value equations. In many cases, an absolute value equation will have two solutions. But in some cases, it'll have no solutions, and occasionally it'll have just one solution.
This video is about interval notation, an easy and well-known way to record inequalities. Before dealing with interval notation, it is important to know how to deal with inequalities. Our first example of an inequality is written here, all numbers between 1 and 3, not including 1 and 3. First, we need to write down our variable, x. Then it is important to locate the key values. For this problem, that is 1 and 3. Now, here we see that x is between these two numbers, meaning we will have one inequality statement on each side of the variable. Here it says not including 1 and 3, which means that we do not have an or equal to sign beneath each inequality. Here we will put 1, the lowest key value, and here we will put 3, the highest key value. Next, we are going to graph this inequality on a number line. Here we write our key values 1 and 3. Because it is not including 1 and 3, we have an empty circle around each number. Because it is the numbers between, we have a line connecting them. The last step of this problem is writing this inequality in interval notation. Writing things in interval notation is kind of like writing an ordered pair. Here we would put 1, and then here we would put 3. Next, we need to put brackets around these numbers. For this problem, it is not including 1 and 3, which means we will use soft brackets. However, if it were including 1 and 3, we would use hard brackets. It is important to note for interval notation that the smallest value always goes on the left and the biggest value always goes on the right. You also include a comma between your two key values. Now let's work on problem B. Once again, we write our variable x. Again, it is between -4 and 2, but this time it is including -4 and 2. This requires us to have the or equal to sign below the inequality. Then we put our lowest key value here and our highest here. The number line graph for this problem is slightly different. We still